What is the main motivation behind the paper?
The main motivation behind the paper is to assess whether popular interpretability tools originally designed for transformers can also be applied to new RNN models, specifically Mamba and RWKV v5 architectures. The paper aims to investigate the steerability of RNNs using techniques such as contrastive activation addition, CAA, and state steering, which were originally developed for transformers. The authors hypothesized that steering with CAA would work on RNNs without requiring architecture-specific changes, and that the compressed state of RNNs would make them easier to steer compared to transformers. Additionally, the paper explores the tuned lens approach to understand how RNN language models make predictions at different layers, similar to the approach used for transformers. By fine-tuning RNN models on specific behaviors and using linear probes, the paper aims to elicit latent knowledge from the models and assess their ability to generalize to unseen scenarios. Ultimately, the goal is to provide insights into the interpretability and behavior control of RNN models, comparing them to the established interpretability tools used for transformers.
How do Mamba and RWKV architectures differ from traditional transformers in terms of handling long sequences?
Mamba and RWKV architectures differ from traditional transformers in terms of handling long sequences by allowing for parallelized training across the time dimension through specific mechanisms unique to each architecture. Mamba utilizes a selective state space model, SSM, in each layer, enhancing its expressivity by allowing parameters to depend on the input, while RWKV makes use of alternating time mix and channel mix modules in its layers. Additionally, Mamba employs causal convolution blocks to route information between token positions. On the other hand, RWKV versions 4 and 5 differ in the type of state they use, with version 4 having a vector-valued state and version 5 having a matrix-valued state. These mechanisms in Mamba and RWKV enable them to handle long sequences in a more efficient and effective manner compared to traditional transformers, making them attractive alternatives for various use cases in natural language processing tasks.
What are the specific behaviors studied in the dataset used for testing the steerability of RNNs?
The specific behaviors studied in the dataset used for testing the steerability of RNNs are coordination with other ICE, corrigibility, hallucination, myopic reward, survival instinct, sycophancy, and refusal. These behaviors were originally introduced by previous works and were further expanded upon in the dataset used for the experiments. The steering vectors were computed based on the differences in the model's mean activation vector at the position of the answer letter for responses matching the behavior and for responses not matching the behavior at each layer of the network. The dataset consisted of pairs of prompts containing two-way multiple-choice questions, with one prompt choosing the answer letter corresponding to the desired behavior and one prompt choosing the opposite behavior.
How is the steering vector computed for RNNs in the paper?
The steering vector for RNNs in the paper is computed by taking the difference in the model's mean activation vector at the position of the answer letter for responses matching a specific behavior and for responses not matching that behavior. This computation is done for each behavior Z and each layer L of the network. The resulting vector, denoted as vec_act_L, is used to steer the RNN model's behavior by adding it to the residual stream at inference time. Additionally, for RNNs, the paper also explores steering with the state, where the state of the RNN is used to generate a steering state vector, vec state. The steering vector is always multiplied by a scalar multiplier, typically between -3 and 3, to determine the sign and strength of the intervention. The steering effects are observed to be most prominent in the middle layers of the models, with different multipliers affecting the steering behavior across layers.
What is the significance of the selective state space model, SSM, in the Mamba architecture?
The selective state space model, SSM, in the Mamba architecture is significant because it allows the parameters of the SSM to depend on the input, enhancing the model's expressivity. This feature enables each Mamba layer to utilize two different mechanisms to route information between token positions: a causal convolution block and the selective SSM. The SSM's ability to adapt its parameters based on the input data enhances the model's capacity to capture complex relationships and dependencies within the sequences it processes. By incorporating the SSM, Mamba can effectively handle information flow between tokens in a more dynamic and context-aware manner, leading to improved performance in tasks that require understanding long-distance dependencies and intricate patterns in the data. The SSM's role in enhancing expressivity and information routing within the Mamba architecture contributes to its effectiveness in natural language processing tasks, making it a valuable component of the model's design.
Explain the concept of state steering and how it is applied in the paper.
State steering is a technique introduced in the paper to control the behavior of RNN models by manipulating their internal state. In the context of the study, state steering involves using the compressed state of RNNs to influence their responses. The paper hypothesized that steering RNNs would be easier than transformers due to their compressed state, and that the internal state could provide additional steering capabilities. The process of state steering involves generating a steering state vector, VEC state, based on the internal state of the RNN models. This steering state vector is then used to guide the model's behavior by adjusting the activations within the model. By applying the steering state vector to the RNN's internal state, the researchers were able to slightly increase the percentage change in behavior. However, it was noted that the effect of state steering is not additive, as the activation steering already influences the model state. The paper also experimented with using state steering to control the content of the model's generation, showcasing examples of steering responses in the context of generating stories. Overall, state steering in the paper refers to the manipulation of an RNN model's internal state to influence its behavior and responses.
What are the differences between the logit lens and the tuned lens in the context of transformer language models?
The main difference between the logit lens and the tuned lens in the context of transformer language models lies in how they handle the intermediate values of the residual stream. The logit lens simply sets the residuals to 0, while the tuned lens involves training a set of affine transformations, one per layer, to ensure that the predicted token distribution at any layer resembles the distribution of the final layer. This means that the tuned lens uses affine transformations to adjust the predicted token distribution at each layer, aiming for similarity with the distribution of the final layer, whereas the logit lens does not involve such transformations and directly sets the residuals to 0. Additionally, the tuned lens was developed to address some of the limitations of the logit lens, providing a more refined approach to decoding the intermediate values in transformer language models.
How are the probes trained in the ELK approach for scalable oversight in the paper?
In the paper, the probes in the eliciting latent knowledge ELK approach for scalable oversight are trained using linear probing methods. Specifically, the authors experiment with 7 different linear probing methods: linear discriminant analysis, LDA, mass mean probing, logistic regression, contrast consistent search, CCS, contrastive representation clustering, CRC, logistic regression on contrast pairs, and difference in means on contrast pairs. These methods take the residual stream at a given layer as input and output a single score. The probes are trained on examples that contain the character Alice in the context to predict the labels. Additionally, as a separate experiment, a feature vector is constructed for each example by concatenating the outputs, log odds, from all the layers of the probes. This feature vector is then used to fit a Gaussian distribution to the easy Alice activations, and the anomaly detection score is calculated based on the distance of a point from this distribution. The performance of the probes is evaluated based on their ability to distinguish between hard Alice examples and hard Bob examples, with a focus on generalizing from easy to hard examples.
What linear probing methods are investigated in the paper for eliciting latent knowledge from the models?
The linear probing methods investigated in the paper for eliciting latent knowledge from the models are linear discriminant analysis (LDA), mass mean probing, logistic regression, contrast consistent search (CCS), contrastive representation clustering (CRC), logistic regression on contrast pairs, and difference in means on contrast pairs. These methods take the residual stream at a given layer as input and output a single score. Probes are trained on examples containing the word Alice in the context to predict the labels. Additionally, a separate experiment involves constructing a feature vector for each example by concatenating the probe outputs from all layers and fitting a Gaussian distribution to the easy Alice activations to use as an anomaly detection score. The paper evaluates the detector's AUROC at distinguishing hard Alice examples from hard Bob examples, showcasing the effectiveness of these linear probing methods in eliciting latent knowledge from the models.
How do the probing results in the paper compare to the findings in BTLM models regarding the effectiveness of probes trained on easy examples with specific contexts?
The probing results in the paper show that probes trained on easy examples with specific contexts, such as Alice, are effective in predicting correct labels even in hard examples with different contexts, like Bob, achieving over 70% OROC, similar to the findings in BTLM models. The probes trained in contexts featuring Alice can predict the correct answer despite the model outputting otherwise, and the same holds true for probes trained in contexts featuring Bob, tasked to predict outputs in Alice's context. The paper's results align with BTLM models in demonstrating the effectiveness of probes trained on easy examples with specific contexts in predicting correct labels, even in challenging scenarios, showcasing the probe's ability to generalize across different contexts and maintain accuracy in determining the correct answers.